Hello, today we will be solving Leetcode problem 1319, number of operations to make network connected. This is a medium level problem and was available through weekly contest number 171. It's also available through the problems page. So let's begin. Basically given a network of n computers, and each computer is labeled from 0 to n minus 1. Now these computers have connections between them. Namely, connections I is equal to A comma B, where A and B denotes a connection between computers A and B. Now we have the problem as follows. Connections is given, and we have to figure out the minimum number of times we can remove an edge between two computers and replace it between two computers that didn't have an edge between them already, such that the network is connected. So each of those removing and replacing is called an operation. And we have to find the minimum number of operations such that the network is connected. If it isn't possible, return -1. So let's look at some examples. In this example, the 3 is not connected. And by connected, we mean all computers can reach any other computer. So almost like an undirected tree. So, except it can be more general because it can have extra loops if you have extra edges. So let's take a look. This 3 isn't connected in the network. So let's take this edge from 1 and 2 and let's replace it here, which is one operation. This is now a connected network. And so we can output 1. As we can see, n is 4 because there's 4 computers and connections. 0 connects to 1 and vice versa, and 0 connects to 2, 1 connects to 2. Now let's take a look at this example, where you have two computers that aren't part of the connection. Well, you can take the edge from 1 to 2, connect it between 1 and 4, take the connection from 0 and 3, and put it over here. Therefore, we get a connected network in 2 operations, minimum. So, let's think, when is this not possible? Well, from data structure theory, we know that the minimum number of edges we need to create a connected graph of v vertices, minimum edges is v minus 1, because that's a tree in essence. So the minimum number of edges we need is v minus 1 in this problem. If we don't have v minus 1 edges, we can't solve it. So imagine you have 3 vertices and you have 1 edge. That's impossible to connect them all with 1 edge. You need 2 at least. So assuming these computers are vertices and the edges are the connections between them, we can see here that n equals 6 vertices, and we have 1, 2, 3, 4 pairs or 5 edges, which means it's fine. So 6 minus 1 and v minus 1 is 5. That's enough. But if we have 4 edges and 6 vertices, that's not enough. We need 5. So we can check the constraints and then start some code. So the constraints seem fairly normal, except there's 2 cool ones. There are no repeated connections and no 2 computers are connected by 1 or more cable. So that's cool. It summarizes that we don't have as much redundancy in here, but the duplicates aren't here. So for example, 0, 1, 1, 0 won't be here. So that's great. It just reduces the size. So let's get started with the fact that we know. So we know that it's impossible if the number of edges we have is less than n minus 1. Therefore, the number of edges is the number of pairs and connections, since the problem said they're unique. So if len connections is less than n minus 1, we return -1. Now let's think of the real problem. So the problem comes down to this. This can be considered as a graph, with computers as vertices, as I said, edges are the connections. So the real problem is how many graphs in this big graph are isolated or disconnected subgraphs in a way. For example, 3 is a disconnected subgraph and 0, 1, and 2 is a disconnected subgraph. Now together you can connect them with 1 edge. So we can connect 2 disconnected subgraphs with 1 edge. Taking a look here, there are 3 disconnected subgraphs or 3 disconnected parts. So 1 part, 2 part, and a 3rd part. So 4, 5, and these. Now you can connect the 4 with this subgraph in one edge, one operation, and then you connect that new super part with the 5 in one operation. So all this is telling us is if we find the number of disconnected subgraphs and subtract 1, that gives us the number of operations we need to do at minimum. So it's summarized over here that for every 2 disconnected subgraphs, we need on one edge to connect them. Therefore, return the minimum number of disconnected subgraphs minus 1. Cool. So now we reduced it to the problem of finding the number of disconnected subgraphs. How do we do that? We do that by noticing something interesting. That problem can be solved using graph algorithms because we already reduced it to a graph problem. Let's try DFS, or depth first search. We do depth first search on let's say any node, 0 for example, and we keep a visited set. Then we can say the following. 0, depth first search, populates visited to 0, 1, and 2. Great. Now when we move on to 1, if it's in the visited set, that means we got to it through a subgraph already, which was the zeros subgraph. And that means we shouldn't think about it. So let's just continue and pretend it didn't happen. 2, same thing, it's already been visited. Let's continue. Now 3 hasn't been reached. And since the depth first search at a node hasn't visited this one, we know this is disconnected from this one. We know that the 3 is disconnected from this subgraph of 0, 1, 2. Therefore, we know that there is one more disconnected subgraph. So we can have a count of number of disconnected subgraphs and count up by 1. And from there, we can search 3 and check all its depth first search, populate visited. And then when we get to another node, we can check if it hasn't been visited, it's yet another disconnected subgraph because both of these haven't seen it yet. And we can continue from there. So we have to perform DFS on every node. And if it's unvisited, add 1 to the counter. Visit it, DFS that node, and loop for all nodes. So we have to do this for every node to verify. For example, here we'll do DFS on 0, it's not visited, number of disconnected subgraphs is now 1. So we visit all of 0's depth first search, and then we move on to 1. It's visited, continue. 2, visited, continue. Same with 3. Now when we get to 4, we say, okay, it's not visited. So now I have to increase my disconnected subgraphs to 2 and visit 4. So now visited is 4. Now 5 is on the way. 5 is unvisited, increase the disconnected subgraphs and visit 5. No more nodes. Disconnected subgraphs is 3 and hence we return minus 1, which is 2, as seen by this. So let's look at the time complexity and space complexity of this approach. For time complexity, we have to perform depth first search on potentially the entire graph, where V is the total number of vertices, or N in this case. And that plus the number of edges, which is the complexity of depth first search for an entire graph. Because we have a visited set, we won't duplicate depth first search. So it's O of V plus E. And another thing to note is we need to also populate an adjacency list or an adjacency matrix to store the values of the graph, to store it as either vertexes to other vertexes or an adjacency matrix. So the way we do that, it depends strongly on this complexity. So we'll take a look at why it's still O of V plus E. In terms of space complexity, we need V space, which all the vertexes for visited, potentially we can visit all of them. And the stack for depth first search is O of V. Now we can use an adjacency list to get O of V plus E space because we have E edges and we have V nodes. Therefore, we have O of V plus E space complexity for an adjacency list. Now, to populate that adjacency list would also take O of V plus E, or in essence, it would just take O of E. So I'll add that in here. And so O of E plus O of V plus E still remains at O of V plus E. And the complexity for space is now, again, O of V plus E. Cool. So let's get started with the approach. Over here, I'm just going to add what I've written before. So I create an adjacency list, and that adjacency list is an empty list for all the vertices, and for each vertice I append to its adjacency list the vertex it's connected to. So of each pair of connections, the first pair append the second pair, and the second pair append the first pair, which means 0 add its existing connections to 1 and vice versa. Now we add the logic of visited. So after we visited, we have a set. So we have also disconnected count, as we said before. And for every vertex, we check if it's not visited, increase the disconnected count by 1, and perform depth first search with changes visited in place. Now, return the disconnected count minus 1, which is all this logic. And so we need a depth first search function. So I'll write that here. My depth first search function is the exact same as similar to my previous depth first search function in my other video, where I start with the stack. And while the stack is unempty, check if the last element of the stack, when it's popped, isn't visited. If it isn't, add it to the visited, and this changes the visited in place. So the set will now be different the next iteration. And so for every other vertex adjacent to this vertex, if it isn't visited, add it to the stack to be examined later. And so we return disconnected count plus 1. Again, I'm going to add this to our time complexity. So we get that our time complexity is O of v plus e, and our space complexity is O of v plus c, which looks very nice for a graph problem. So let's run our code. And we get 1 and 1, which is nice and promising. I always like to run the code before submitting. And we get our submission as 94.44% faster than Python solutions, 100% faster and better in space solutions, so less memory. So that's a very nice result, very promising, and again, it looks like a great problem. So we've just tackled number 1319. Thank you for watching. I urge you to strongly understand this code, and there can be many other ways that you can solve this problem. So please reach out in the comments below and let me know how you solved it. Thank you very much, and have a nice day.